Good morning, Calculus 3 gang. Wanted to dive into section 12.5 with you. As if double integrals weren't enough, today we get to talk about triple integrals. So let's recall for just a moment the setup for double integrals, and that will help us understand triple integrals, hopefully. So for double integrals, a couple of key things. You have a function of two variables. Double integrals, function of two variables, right? How do we interpret them? Well, a function of two variables gives me a surface in 3 space. So here's my surface. We'll just work over a rectangle today. If I want to do a double integral of this function over this rectangle, the idea was that you can break up the rectangle into a grid of little boxes. I'm going to do this very loosely because I just want to communicate some ideas, not precision. For each one of those little boxes, you pick a test point. Maybe I pick that test point for this little box right here. I plug that test point into my surface, and that puts me up here. And then I now have a height. So I multiply the area of this little box right here times the height, and you can interpret that as the volume of this box. I'm having a hard time drawing it nicely, but the volume of this box like that. And so double integrals, I'm going to write this loosely. It was a limit of a sum of these boxes where you, for every box, you multiply by the area of the box, which we usually write delta A, and then you want to multiply by the height, which was our test point. We usually wrote xi star, yj star, and then if you index the number of boxes by I and j, here we go. Let's say I equals 1, j equals 1 to, I don't know, n and m. Then we're having n and m shooting off to infinity. So this is quite literally saying take the limit as the number of boxes, little rectangles, goes to infinity, where you're adding up the area of each box times the height of the function. And of course, you can interpret double integrals as volume when your function lives entirely above the xy plane. So I want you to have two things in your mind as we go forward. Double integrals, functions of two variables. You interpret double integrals as volume. Okay, so pause the video and say that to yourself if you want. Double integrals, functions of two variables. We interpret double integrals as volume. All right. Now, when we dive into triple integrals, if double integrals involve functions of two variables, then you can tell me triple integrals involve functions of three variables. And whatever it is, it's not going to be volume anymore. Triple integrals in general, we'll see how to compute volume with them in certain cases, but in general, triple integrals are not going to simply be interpreted as volume. Here's the basic idea. You start with a solid in 3 space. For double integrals, we started, I'm going to scroll up slowly here so as not to make you seasick. For double integrals, we started with a region, a piece of area in 2 space. For triple integrals, we start with a solid in 3 space. Just like we broke up our little region into rectangles in 2 space, we break up our solid into little 3D boxes in 3 space. So here's a picture of one of those little boxes, and you can sort of see change in y, change in x, change in z. All right, in each box, we're going to pick a little test point somewhere in there, and we're going to plug that into our function, which is going to be of 3 variables. So I'll have an xi star, yj star, and zk star. And all of a sudden, you get a sense of how this is going to go. This is going to be a sum of the volume of this box times whatever this is. And so this is like 4-dimensional volume. This is actually hypervolume. So somehow triple integrals, without any further explanation, you can think of them as hypervolume. Let me write down the technical definition for you. So here it is, just in case you want to see it. The triple integral over this box B is of some function of three variables, f of x, y, z. By the way, instead of writing dA here for double integrals, we write dV. The dA was saying, look, multiply f times a little piece of area for double. For us, we're multiplying f by a little piece of volume. So we write dV. And we interpret this as a limit. This is the limit as L, M, and N all shoot off to infinity of a triple sum. Oh, yes, so much fun. K equals 1 to N, J equals 1 to M, L equals 1 to, I equals 1 to L, pardon me. I got so carried away that I mixed up my letters there. And then what do? You're multiplying for each one of these boxes. You're plugging in a test point. I'm going to hardly have enough room here. Let's zoom in, and hopefully I can squeeze it. ZK, and then we want to multiply by a little piece of volume, dV. So I squeeze it in there. You don't need to know this technical definition for this class. Our goal, sadly, is not to just revel in mathematical rigor and mathematical beauty, but rather to actually learn how to do useful things, which is good. It's good to be able to do useful things. But that is the basic idea. What is this sum actually saying? What does this mean? Okay, just to fly over basic idea. This is just saying add up all the boxes. So add up, sum, the volume of each little box times plug in a test point from the box into F. And then keep doing that as the number of boxes. This is just saying the number of boxes goes to infinity. So finer, finer, finer. Okay, so that's the basic setup. What do you do with this? And how do you compute these? That's our next question. So let me scroll down to an empty page here where I can write down some things. So our first result, I meant to write this ahead of time, but I'll have to write it out. So our first result is Fubini's theorem for triple integrals. And actually, to save time, I'll stop this video here, and in the next part, we'll pick it up right here. That way you don't have to watch